And if that turns out to be not the case, you should let me know. Okay, so I will presume that you can see this and that you can hear me, and I will get started. So first of all, thank you for the invitation to speak. And thanks a lot for swapping me into a slightly earlier time. This is much nicer than talking at 2:30 in the morning, which would have been an interesting experience for me. And let me get started right away. So my job is to tell you about neutrino physics, and I'll try to tell you a little bit of what's been going on in neutrino physics from an incredibly biased perspective. So hopefully you can put up with that. And in the end, I hope to say a couple of things that are useful. And I don't know how the Q&A is working out, but I presume that the questions will be at the end. If somebody wants to ask anything in the middle of the talk, that's still okay. So just to get everybody on the same page, our understanding of neutrinos has changed qualitatively in the last couple of decades. This came about with the discovery of neutrino oscillations. This is a very well-established phenomenon. It is a fact. We've been able to see neutrino oscillations from lots of different places, using neutrinos produced in lots of different ways. And we've been able to see this phenomenon with electron neutrinos and muon neutrinos. And we even have some data on tau neutrinos as well. If you take all the data and you combine everything, the only explanation we have for all of the observations is that neutrino masses are not zero and that leptons mix. So this here is a very well-known plot, which I like very much, so I'll say something about that. This is a plot of all of the charged fermion masses in the Standard Model, combined with the information that we have on the neutrino masses. And the key information that I want you to get out of this is, first of all, we know now that at least 2 of the neutrino masses are not zero, which by itself is an interesting discovery. And that's mostly what I want to talk about. The other bit of information is something that is also quite obvious and people spend a lot of time on, which is, while neutrino masses are not zero, they're very, very small. And that's something we've been trying to explain. I want to try to get my clock going so that I have some control over time. But the point is, neutrino masses are very small compared with the masses of all of the other fermions. We don't know if that means anything, but we spend a lot of time thinking that it means something. From a big picture perspective, just the fact that neutrino masses are not zero are sort of a big deal for us, because they imply, and I would argue for the first time, a phenomenon that the Standard Model fails to explain, which happens at the laboratory level. I want to say a little bit more about this, and people can talk to me about, they can ask about this later, but it's a very simple statement that I can make, is that if you take all of the known fields that make up the Standard Model, which are the fermion fields and the Higgs boson, and you take all of the gauge interactions into account, you can actually make a prediction. And the prediction that you would make is that neutrino masses are exactly zero. Now, neutrino masses are very small, but they're not exactly zero. What that means is that if you want to include neutrino masses into your model, you need new ingredients. They're new degrees of freedom that we didn't know about before, but we know must be there because they have to explain why neutrino masses are not zero. It turns out that we don't know what these new ingredients are, but because we've been thinking about this for a few decades, we have a long list of what we think the options are. So a lot of the work that we do is to try to figure out, amongst all the different options for how neutrino masses come about, which option is the right one, and what are the new particles that must exist in order to explain neutrino masses are not zero. Now, this is a very big deal, and I don't need to remind you of that, but I'll do it anyway. Because as you know, in the business of fundamental particle physics, we're always trying to take our current understanding of the model or of particle physics phenomena, and we're asking, what are the phenomena that we fail to explain? And the hope is that by explaining these other phenomena, we get an enhanced and improved understanding of fundamental particle physics. If you ask yourself, what is it that the Standard Model of particle physics does not explain? The number of things that it doesn't explain is actually very small. So this is included here in this slide. And just as an example, for a very long time, we didn't really know the physics behind electroweak symmetry breaking. We knew that electroweak symmetry breaking had to happen, and we had a good idea of how it happened via some Higgs mechanism, but we weren't sure until actually we got data from the LHC that told us that the Higgs boson existed, and that reveals for us that the vanilla, standard model explanation of electroweak symmetry breaking, if it's not absolutely true, it is definitely a very good approximation for what's going on. Now, the other phenomena that we don't understand, that fundamental particle physics or our current understanding of particle physics fails, all have some astrophysics and cosmological origin. And they're not the subject of my talk, but I'll mention those anyway. One is a dark matter puzzle. The other one is a problem of baryogenesis. And finally, the last one is this mysterious behavior of the expansion rate of the universe that seems to be accelerating today. So all of these things are probably facts, and all of these things seem like particle physics problems, but none of them can be addressed given what we know about the fundamental particles today. So they all call for new degrees of freedom, new interactions, or maybe a new way of looking at particle physics. So neutrino masses are part of this very select list of things that we don't understand very well. Now you can ask yourself, how do you give neutrinos a non-zero mass? The short answer is we don't know. And it's not like we can't think of good ways of giving neutrinos a non-zero mass. The best way of thinking about this is that we can think of too many different ways of giving neutrinos a non-zero mass. And of course, all of these different ways succeed in explaining the data that we have today. And our job is to try to figure out which one of these ideas that we have is correct. And of course, in order to solve this puzzle, we need more experimental data. So right now, if you look around in the realm of particle physics, neutrino physics is in this very strongly data-driven mode, where we know we need more data. We don't know exactly where the data will be coming from, so we kind of look everywhere, hoping that something will happen, and we will learn more about how neutrino masses happen. So most of my talk will be discussing some of these ideas that people have thought of that explain non-zero neutrino masses, and I'll also talk a little bit about what kind of probes do we have in mind and what sort of surprises might happen. So I am required to talk about the simplest idea we have for non-zero neutrino masses, and that's to look at the standard models and effective theory. If you look at the standard models and effective theory, the statement you're making is that if you get to a certain mass scale, you will run into new degrees of freedom. You have to integrate those degrees of freedom out, and at low energies, they look like effective operators. If you write down generic effective operators, the first one that you run into is a dimension pointed out a very long time ago by Weinberg. And if you ask yourself, what are the experimental consequences of this Weinberg operator, which is this operator here, at low energies, it turns out that the prediction that you would make is that this operator leads to non-zero neutrino masses. You actually get a neutrino mass that's parametrically smaller than the charged fermion masses. And if you stop for a second, you see that this is a great match to the observations that we have. Neutrino masses are not zero, and they look qualitatively smaller than the charged fermion masses. If you start asking more questions of this idea, the other interesting thing that jumps out at you is that lepton number is violated. Because in this, if this is how neutrinos get a mass, the neutrinos actually get a Majorana mass, which means that lepton number is not a good quantum number of nature. We can also ask, what's the effective scale that the neutrino masses are pointing to? And the effective scale lambda is around 10 to the 14 GeV, which is a seriously big number. If you think about the types of experiments that we do today, they're sensitive to things that are around the TeV or below. So this is sort of a science fiction-like energy scales, and it's actually very close to the gut scale. Now we have to pause and ask, what else do we get out of this understanding of neutrino masses? And the answer is we don't know, because it depends on the ultraviolet physics that ultimately manifests itself as this higher dimensional operator. So there's a lot of work that goes into understanding how do I realize this higher dimensional operator? So what are the new particles that I'm integrating out? And how do I convince myself that that particular way of realizing this effective operator is the right way to do it? I don't want to spend a lot of time talking about the three-level realization of this, because that's something that's become very familiar. It's called the Seesaw Model. It's actually models. There are three models of this. There are three kinds of particles that you can integrate out at the tree level to realize this dimension 5 operator. But I do want to point out that if you do have a three-level model, your effective scale of the operator is of order the mass of your new heavy particle divided by the coupling of this new heavy particle to standard model particles. And it's interesting that we need this number lambda to be very large. We need it to be 10 to the 14 GeV, but there are different ways of getting to 10 to the 14 GeV. And I'll say something that's completely obvious, but it's important. And the options are that maybe the masses of the new particles are very heavy. Maybe they are of order 10 to the 14 GeV, in which case the coupling between the new physics and the neutrinos is large, but the new physics is very heavy. A qualitatively different choice is that maybe the neutrinos are very weakly coupled to the out to be the case, then the new physics doesn't have to be very heavy, just has to be very, very weakly coupled. And that's another way of generating this 10 to the 14 GeV effective scale out of a physics that doesn't have to be super heavy. There's actually a third option, which is because there are different neutrino flavors, this is actually a matrix equation. So it is possible to have a matrix multiplication in such a way that neither the couplings are very small, nor the masses are very big, but somehow the matrix multiplication has some cancellations in it, and it looks as if the new physics is much heavier than it actually is. There's actually another way of realizing this Weinberg operator, which is you don't have to do it at the tree level. You can do it at the loop level. People have been talking about this for a very long time. So there are lots and lots of models where you break lepton number at some mass scale. The neutrinos only learn about this at the quantum level. And that nonetheless leads to non-zero neutrino masses. These models are more involved. They have different kinds of particles in it. You can argue that they're kind of uglier. But on the flip side, the effective scale associated to them is qualitatively different from what you get out of the regular sort of tree-level seesaw mechanism that everybody's familiar with. There's a clever way that many people have been exploring in order to discuss very generically what's the phenomenology of these types of models. And the idea is to use an effective operator approach, an effective field theory approach. And the idea is actually very simple. You assume that you have some new heavy particles, and you assume that when you integrate them out at the tree level, you generate some effective operator that violates lepton number by 2 units. With this effective operator in mind, you can construct the Weinberg operator or the dimension 5 operator at the loop level, only involving standard model loops. And by doing that, you can learn about a lot about the classes of models that you can think about by identifying all the possible higher dimensional operators that you can run into, and using this effective field theory approach to ask questions about which models have which effective scales associated to them. This is a very bold process. It doesn't have to work. It doesn't always work because we make some simplifying assumptions along the way, but it's a great way of qualitatively describing lots and lots of different ways of generating non-zero neutrino masses. So I want to give you an example of that. So here in this slide is a list of all dimension 5 operators that violate lepton number by 2 units, all dimension 7 operators that violate lepton number by 2 units, and all dimension 9 operators that violate lepton number by 2 units. And people have done this also at dimension 11. At dimension 11, the list is kind of long, and we didn't want to write it down. And what we can do with this is that we can ask, what's the effective scale of this operator in such a way that I get the right neutrino masses at the end? This is what's plotted here in this histogram. The idea is, if we take the 3-level models, the effective scale associated to them, as I've talked about already, is about 10 to the 14 GeV. So that's this point all the way out here. On the other hand, if I take a different model that only generates neutrino masses at the loop level, sometimes at the 1 loop level, sometimes at the 2 loop level, 3 loop level, 4 loop level, it depends on the operator, the associated effective scale that you extract by matching the scale of the operator to what we know about non-zero neutrino masses is very, very different. And it varies all the way from some seriously big numbers like 10 to the 12 GeV, all the way down to the 100 GeV level, and even less than that. And the reason this is exciting is that if you happen to have an effective scale that's very high, unless the new physics is very weakly coupled, the new physics is also very heavy, so it's very, very hard to study in laboratory experiments. On the other hand, if your new physics generates a certain effective operator at the 3 level, and you insist that that new physics gives you non-zero neutrino masses, then you can look for the new physics in a large variety of different types of experiments that we're familiar with that range from EDMs to charged lepton flavor violation, all the way to collider experiments like the LHC. So if you're in the business of identifying falsifiable neutrino mass models, these types of models here are very interesting because they should leave an imprint in different types of particle physics experiments. And on top of that, they have different types of new particles in them. And those new particles might be good for something else. I want to give a very simple, actually not simple, very complicated example of this. So imagine that I have a bunch of new physics particles that when I integrate them out, I generate at the 3 level this dimension 9 operator that only has SU2 charged fermions in it. So this is we call it the all singlets operator. And if you ask yourself, how does that lead to a non-zero neutrino mass? The answer is it does that at the 4 loop level. So it's this operator here. It's this kind of diagram. And your prediction for the neutrino mass looks something like that. And this turns out to be a really crappy model. Because if you want to explain non-zero neutrino masses, your effective scale of the operator has to be some super low number like 1 GeV. The reason this is interesting is that in this model, the contribution of the lepton number violation physics to neutrino masses is so small that it's very, very likely that this is what nature is doing at some level, that we should be able to see this physics, even though the neutrino masses are very small. So that was the kind of game that we were playing. I just want to give you an example of what kind of physics you have to worry about. And of course, it depends on the UV completion of this. What's nice is that we can actually calculate all the UV completions of this model. They diagrammatically look like this. Dashed lines are scalars or they're bosons, and solid lines are fermions. So you need some new bosons or some new combinations of bosons and fermions to generate this effective operator at the loop level. Generate this effective operator at the 3 level and generate neutrino masses at the 4 loop level. And it's kind of fun to play this game. And the types of particles that you need to do this are written down here. and their quantum numbers are here. And you notice that these are very different types of particles. Some of them have strange charges. Some of them are colored. There's a whole bunch of color sextet objects. Some of these objects have baryon number. And I'm not advocating that this is an interesting model. It's actually lots of different models, but it gives you the sense of the story, which is if you want to give neutrinos a non-zero mass, you need new degrees of freedom. And the quest of understanding non-zero neutrino masses is really understanding, are these, do these new degrees of freedom actually exist? And as an example, these new particles mediate a whole bunch of different phenomena, including mu-to-E conversion in nuclei, mu-to-3 electron decays, and bar mixing. And we've kind of worked through the phenomenology of all of these models. And it's sort of entertaining that even though these models violate lepton number and they give the neutrinos a non-zero mass, the generating neutrino mass part of the story is not very important. What is really more important about these types of models is that they give you very large signatures at flavor experiments, at baryon number violating experiments, and even collider experiments. And again, the story here is not to sell you the model, but just to tell you that there's a whole zoo of different possibilities that we can consider for generating non-zero neutrino masses. And they can point in very different directions depending on what nature has chosen to do to make neutrinos be massive. I want to say a few words about another topic that's often forgotten, is that in everything that I've talked about so far, I've assumed that the neutrinos are Majorana fermions. The neutrinos could be Dirac fermions. And I want to skip this particular slide. But it's interesting that there's nothing wrong with neutrinos being Dirac fermions. It turns out if you add a right-handed neutrino field to the model and you say that lepton number is a conserved symmetry of nature, then the neutrinos are going to be Dirac fermions. And there's absolutely nothing wrong with that. The reason we don't like this is usually aesthetic, and it has different pieces to it. The one which I like the least is the fact that people often say that what this model doesn't do very well is explain why the neutrino masses are so small. In order to get a non-zero neutrino mass with the right value, you need a new Yukawa coupling, which is of order 10 to the minus 12. And people tend to believe that 10 to the minus 12 is a very small number, which is true. It doesn't mean it's wrong. I should remind you that the electron Yukawa coupling is about 10 to the minus 6, and that's a pretty small number. And even though we've tried to explain why the electron Yukawa coupling is 10 to the minus 6, I think it's fair to say that we don't have a compelling explanation for that. And even if you have your own favorite explanation for that, I think it's fair to say that there's no experimental verification that the Yukawa coupling of the electron just isn't what it is because that's what it is. So tiny Yukawa couplings for the neutrinos they make us uneasy, but they're not wrong. I do want to say that there are ways of explaining why neutrino masses would be associated with tiny Yukawa couplings. And the simplest explanation is to postulate, for example, there's this right-handed neutrino field. And if the right-handed neutrino field has any new quantum numbers, you invent a new quantum number that the right-handed neutrino has. One consequence of this quantum number, assuming it's not shared by any of the other standard model particles, is that the neutrino Yukawa coupling is forbidden. So if you do have a right-handed neutrino field, and the right-handed neutrino field has some unknown gauge symmetry associated to it, so it has some quantum number that we don't know about, then the neutrino Yukawa coupling is naturally forbidden, which is interesting because you predict that the neutrino is supposed to have zero mass, in spite of the fact that there's this object in your theory that kind of looks like a right-handed neutrino from the standard model point of view. What this means is, if this new quantum number is broken, I can get a neutrino Yukawa coupling that comes from something like a higher dimensional operator. I mean, it comes from a higher dimensional operator. And after the symmetry breaking of both the standard model and the new gauge symmetry that I've invented, the consequence of that is that neutrinos get a non-zero Dirac mass, but the Dirac mass is suppressed in the sense that it's a consequence of a higher dimensional operator. This is an idea which is relatively old, but it's always worthwhile investigating because new gauge symmetries that only a few particles feel are very popular right now. So hidden sector theories, or theories with a dark Z boson, or theories with a dark photon, they're sort of a revival of these theories in the context of dark matter. So it is possible that the right-handed neutrino is a friend of the dark matter that's also charged under some new dark gauge interaction, and that the neutrinos are actually Dirac fermions, and the smallness of the neutrino mass is associated with the fact that it's the only Yukawa interaction that requires both breaking of the electroweak sector and breaking in this hidden sector. So that's just something I want to say about Dirac neutrinos. So the main message that I want to convey out of this part of the talk is neutrino masses are not zero. We have lots of good ideas to explain why neutrino masses are not zero, but we're very far away from being ready to experimentally verify which idea is correct. I have a very, very long list of things that could teach us about non-zero neutrino masses. And I think it's very important to appreciate the fact that none of these things are guaranteed to tell us something about non-zero neutrino masses. So again, there's no guarantees here, but we've identified all kinds of different observables that have the potential to tell us something about non-zero neutrino masses. So we're all, eagerly awaiting for new charged lepton experiments, new neutrino experiments, cosmology data, and information that will come from these sectors has the potential to tell us where neutrino masses come from. However, I do want to spend the last 15 minutes of my talk reminding you of the obvious fact that we've only seen non-zero neutrino masses in one way, which is neutrino oscillations. So we've been trying to see evidence of non-zero neutrino masses for a very long time in all kinds of places, but the only place where neutrino masses have shown up is in neutrino oscillation experiments. So it stands to reason, and this is not a theorem, but it's just sort of a simple argument, but it stands to reason that if you want to learn more about neutrino masses, doing neutrino oscillation experiments is probably a good idea. So I want to shift gears and say something about that. So as everybody knows, if you take all of the neutrino oscillation data, it can be explained by postulating that the neutrino flavor eigenstates are linear combinations of the neutrino mass eigenstates, and that the neutrino mass eigenstates have different masses. The coefficients that parameterize these linear combinations combine into a unitary matrix that has lots of different names. It's called the PMNS matrix. It's called the neutrino mixing matrix, the leptonic mixing matrix. And it's just a unitary matrix. It's very similar to the CKM matrix. And that's parameterized by 3 mixing angles and at least one phase, depending on whether the neutrinos are Majorana or Dirac. If you take all of the data that you have, that we've accumulated in the last 20 years, and you sort of shake it and you ask, what should these parameters be? The answer is that, first of all of the data fit really, really well, with a few exceptions that I will not talk about at all, these so-called short baseline anomalies. But if you throw those data out, everything else fits very, very nicely. And if you stare at this very, very long table that I have here, it reveals that not only do we explain everything very well, we actually get to measure almost all of these mixing parameters exceedingly well. So most mixing parameters nowadays are known at better than the 5% level to the 10% level. And for people that are older, like me, you are supposed to be impressed by the statement, because if you remember, 30 years ago, we didn't even know that neutrinos had mass. So we didn't even know that any of these parameters were physical. So we went from not knowing whether any of these things were physical to actually measuring them at the 5% level, which is really, really impressive. And it tells you that this field has been evolving very, very quickly. Now, you can ask whether we're done doing neutrino oscillation experiments. The answer is no. There's a lot about neutrino oscillations we still don't know. And I don't want to concentrate on talking about this too much, but I do want to say that we have gotten to a point in neutrino oscillation experiments that we're not just in the business of measuring a whole bunch of parameters. We have enough data now, and we will definitely have enough data in the future to not just measure these new parameters, but to over-measure these new parameters and to start constraining this very simple idea that neutrinos have non-zero masses, but they only have weak interactions, and testing this idea and asking if there's anything that we've left out, or if there's any new phenomenon that we can still run into. So I like to say that the job of neutrino oscillation experiments is not to answer these questions that are written here on the right-hand side. Our goal is actually much bolder than that, which is we want to ask if the formalism that we've developed is correct. And I want to remind people of this very famous picture, which is we've done this, or we've asked this question in the quark sector, and we've been working on this for about 40 years. So again, this is a measurement of CKM parameters. There's two parameters, rho and eta, and there's a whole bunch of colored lines here. And for the younger people in the audience that have never seen something that looks like this before, every colored line is a different measurement of the same parameters. And your first reaction might be, this looks like a waste of resources because you're measuring the same parameters in 20 different ways. But that's not the point. The point is to ask if our theory is correct. And if our theory is correct, then all of these observables have to point to the same place in this parameter space. If our theory is wrong, then these different measurements of the same parameters don't need to point to the same place. As a spoiler, all of these measurements actually point to one place, which is right here. This was true in 2009 when I copied this plot. If you look at the current version of this, it looks nicer than this one, but we still, but the model seems to be correct. So the job we want to do in the lepton sector is the same. So we would like to make the equivalent of this picture and ask if our understanding of neutrino mixing and neutrino masses is correct, or if there's any ingredient that's missing. I just want to say that we have not done a very good job of this yet. I don't want to spend too much time on this, but if you stare at this matrix that I wrote down, we have done very, very non-trivial checks of this matrix. And for people that are sort of experts in the field, we've mostly only measured the magnitude squares of this particular row here of the matrix. We've also measured the magnitude squares of this particular column of this matrix, and that's pretty much everything we've measured. We don't have a lot of information on whether unitarity is conserved or not. We don't have all kinds of non-trivial checks. We have very little information on these elements of the matrix. So there's still a lot of work to do. And we're hoping that the next round of oscillation experiments will add a lot of information in that respect. So it is fair to ask, what could be wrong in our current understanding of neutrino oscillations? And the answer is a lot. And here's a list of the standard suspects that people talk about. So what could happen that would lead to our current understanding of oscillations to be incomplete? And some ideas that people have talked about is that maybe there are more neutrinos. So if there are more neutrinos, then the mixing matrix is not a 3x3 matrix, but it's a bigger matrix. Maybe neutrinos have more interactions than we know about. That changes the way in which we interpret neutrino oscillation data, and that would show up in our extraction of oscillation parameters being incorrect. It is possible that neutrinos have other properties that we haven't taken into account. For example, they might have a non-zero magnetic moment. They might have a finite lifetime. By the way, in the standard model with non-zero neutrino masses, neutrinos do have a non-zero magnetic moment. The heavy neutrinos do have a finite lifetime, but these things are not supposed to be observable. Of course, neutrino oscillations is an interesting phenomenon unto itself, and it is sensitive to weird stuff, you know, violations of the unitary evolution of quantum mechanical states, violations of the CPT theorem. And all of these things can show up in neutrino oscillations. Again, I'm not advocating that they will show up, but they might show up. And what's exciting is that our experiments are beginning to be sensitive to stuff like that. I will briefly just mention one example. So imagine that you invent a new neutrino. If you invent a new neutrino, then your mixing matrix is bigger. There's more mass parameters. And the question is, are neutrino experiments sensitive to that? And the answer is yes. So for example, this is a simulation of what the Boon experiment might see in the near future. And all on the top, you have this black line, and on top of it, there's a blue line. And the black line is what you expect if you only have 3 neutrinos. The blue line is what you get if you have more than 3 neutrinos in a way that's not ruled out by current experiments. So that means that this type of physics could show up in the next round of experiments. And we've done some simulations of this. I don't want to dwell on this too much, but I do want to say that the next round of experiments can not just identify that these new parameters are there, but it can also measure the new. And one thing I want to very quickly mention is, if you have more neutrinos, you have more sources of CP violation. So the number of CP violating phases is bigger than 1. And it is possible to measure these new CP violating phases. That's what's shown in this plot over here. And again, this slide has too much information. I don't want to talk about that. The last thing I want to just mention, because I've been thinking about this and we did some recent work on that, is there's an exciting new thing that we've never done very well yet, which is to study tau neutrino appearance. Again, we do a good job of studying nu mu disappearance and nu e disappearance. We're starting to look at nu mu to nu e oscillations, but we haven't really seen a lot of tau appearance experiments. So this is something that will change in the future with the Boon experiment. The Boon experiment is expected to give you a pretty big sample of tau neutrinos, and you can ask interesting questions with that. So here, by the way, this is what the oscillation probability looks like. And the tau neutrinos require high energies. But this is probably the last plot which I want to mention. And this is a description of everything we can learn about neutrino oscillations one channel at a time. So let's say we do the Boon experiment. And by looking at nu mu disappearance, we can make a measurement of one element of the mixing matrix very precisely. That's here in red. Okay, this is how well we would measure this effective mixing angle and the delta m squared, which is the oscillation frequency. By looking at nu mu to nu e oscillations, we can measure another effective oscillation parameter, and the allowed region of the parameter space is over here somewhere. What's interesting is, this gives us no information on another element of the mixing matrix, which is the tau3 element of the mixing matrix. But with data from the Boon experiment, I can actually make that measurement. Just by looking at tau appearance, I can measure another effective mixing angle and the new oscillation frequency. And the error bar that I get is this really gigantic error bar here. That means that this is not a great sample. But on the flip side, it gives you information that you don't access in any other way, and it allows you to do a unitarity test of the mixing matrix at the 5% level. This is not something we can do today. Our data today cannot do this, and the only reason we can do that is that we have access to a new oscillation channel, which is the tau neutrino appearance. So this is something that I'm excited about, and it's also something that the experimental collaborations are starting to spend a little bit more time on to ask, we're going to have 200, 300, 400 tau neutrinos at the end of the day. What are they good for? We've done a lot of work on this, and I want to skip that because I have, I think I'm starting to run against the time. But I just want to summarize and then take questions. So again, the story that I try to tell you is a very simple story. Something very exciting happened in neutrino physics at the turn of the century. We found out that neutrino masses are not zero. That's great. And we did that through neutrino oscillations. And for the last 20 years, we've been improving our ability to measure neutrino oscillations qualitatively year after year. And we've embarked in another decade of very, very exciting neutrino oscillation experiments. On the flip side, even though we know that neutrino masses are not zero, we still know very, very little about the new physics that leads to non-zero neutrino masses. And again, this is a dramatic statement. We don't even know the scale of the new physics. The new particles can be very, very light. Maybe the neutrinos are Dirac fermions. The new particles can be at 100 GeV. They can be at 100 TeV. They can be almost all the way at the gut scale. And we don't know what the right answer is. The features that we try to explain and the drivers for our models are still relatively qualitative. We know that neutrino masses have to be very small. We don't know why that is, but we take that to be a big guiding principle. The other thing which I didn't talk about is that neutrino mixing is very weird. And I think José Valli is giving a talk at the end of the week, and he will talk about the underlying flavor structure that might be revealing itself in neutrino mixing and a couple of other things, I think, on Friday. So he will talk more about this. And I think the final message that makes neutrino physics very exciting, at least for me, is that we need more data. And more data is coming. So this will remain a very interesting, vibrant field, I believe, for quite a while. So I will stop here. Thank you.
There's one question from the online participant. Could you first answer that question?
Yeah, so let me look at the question, if I can find it. It's in the Q&A, right?
Okay, there's no question from the.
Oh, I'm sorry, I don't see any. Sorry, I apologize. My mistake.
Okay.
Could you comment on the short baseline anomaly, like the mini Boon, something like that?
Yeah, that's a very good question. So I mentioned this only very, very briefly, but there are three types of experiments that don't fit into this picture. That includes the mini Boon experiment and the LSND experiment. And what these experiments do is they have a source which is mostly muon neutrinos, let's say, and they see evidence for electron neutrinos. And the most naive interpretation of that is that somehow the muon neutrinos are oscillating into electron neutrinos. The problem with this interpretation is that the oscillation length is very, very short, which means that you need a new delta m squared. You need a new oscillation frequency. And that indicates the presence of new neutrino states, which is great. So people are very excited about this. The reason we're less excited about this is that we have done a lot of experiments. And if you see new mu's oscillating into new e's, you must necessarily see new mu's disappearing at the same oscillation frequency. And you must see new e's disappearing at the same oscillation frequency. And it turns out that those amplitudes are related to one another. So by combining other experiments that we have done that don't see the disappearance of muon neutrinos and don't see the disappearance of electron neutrinos with the evidence that we get from mini Boon and LSND, they don't match. So I think it's fair to say that that hypothesis is ruled out. So if you just add a new neutrino state into your model and you ask if you can fit also the short baseline anomalies? The answer is you can't. Now, we don't give up. It just means that life is harder. And again, people are exploring different ideas that would explain the mini Boon data or the LSND data or both in a way that's still consistent with all the other observations that we have done. It is fair to say that there's some interesting ideas in the market, but none of them are super compelling, and they're all in the process of being tested experimentally. I think that, what's the best answer for this is that we have new experiments coming online, mostly at Fermilab, and these experiments are very good at testing a lot of these new hypotheses that people have done. And we're all looking forward to that. We will get a lot more data from things like the microboon experiment, the Icarus experiment, and the SBND experiment. This is coming in the next 2 or 3 years. And we're hoping that this will really help us resolve what's going on in that sector there. Finally, the last comment I do need to make is that these experiments are hard. And it is not outside the realm of possibility that there's something that we have missed that is more mundane, that explains what's going on in these experiments. It is fair to say we don't have a great explanation that is, a systematic effect or something that the experimentalists missed. I don't think people have identified a specific problem, but I don't think anybody is capable of ruling that out either. So we need better data. There are more data coming online. I should mention, the other thing that people worry about is reactor neutrinos. It turns out that the flux of neutrinos coming from a nuclear reactor is smaller than what we anticipated. That can also be explained with neutrino oscillations. This is not in trouble because if you don't like mini Boon and LSND, you can still explain the reactor anomaly with neutrino oscillations. And the good news is we're getting very good at doing reactor neutrino experiments. And people are doing these short baseline reactor experiments to learn a lot more about the flux of neutrinos from a nuclear reactor in the hopes of verifying if this reactor anomaly has anything to do with new neutrino physics or not. Again, understanding the overall flux of nuclear reactors is very hard, as I believe some of you in the audience probably know better than me. And I think that the lesson at the end of the day will be that we will know way more about the flux of neutrinos coming from a nuclear reactor. I don't think we'll necessarily learn some new physics, but we will have a lot more information about this tool of using nuclear reactors to do fundamental physics.
I have a question about your very simple model, then some turn into complicated model. There, you have a dimension 9 operator. And
yes,
you do the loop integral become the neutrino mass become 1/λ. So you need to do something. But then I suppose that you are doing this cutoff integral on the loops. So how you can do this cutoff loop integral with all those high dimensional operators? Usually people do this dimensional regularization. You will get a much better sort of situation. Your comment?
So I didn't catch all of that, but I guess you're worried about the UV cutoff of this theory. So can you make a summarized version of the comment again?
This is dimension 9 operator.
Yes.
Yeah. So what I would say is you cannot use a cutoff or integral to do loops.
Okay, good. So that's a fair question. So the statement I'm making is I have a proper renormalizable theory at some very high energy scale. And then I integrate out the heavy modes and I ask what's the effective theory at low energies. This is not dependent on renormalization procedures or anything like that. It's sort of like asking, looking at the weak interactions, and the weak interactions are the exchange of the W boson at high energies. but I can integrate out the W boson, and I have the Fermi theory. So the dimension 5 operator that I have here is the equivalent of the Fermi theory. And we know we can do calculations at low energies with the Fermi theory perfectly. That has no problems at all. But we also know that the Fermi theory breaks down at some mass scale. You know, by the time you get to the W mass, you see the W boson and the Fermi theory breaks down. So the game we're playing is very similar. We have this dimension 5 operator. It explains low energy phenomena, but we know that this theory has to break down at some mass scale. What we're trying to do is to guess what that mass scale is. And the point that I'm trying to make is that guessing what the mass scale is very difficult, because you can run into things in between, and they can change your picture qualitatively. I don't know if that answers the question.
Well, okay, so I understand what you are doing.
Okay.
Okay, so let's thank Andrew again for this very nice talk.